Welcome. Today we will continue with linear regression. Today's topic is sampling distribution of regression coefficients. So, what we will cover in this lecture: sampling distribution of regression coefficient, test of individual regression coefficient and group of coefficients, confidence interval on the individual regression coefficients. So, let us now start with the regression equation. You have already seen that the linear regression equation is y equal to x beta plus epsilon, where beta we have k plus 1 beta values like beta 0, beta 1 to beta k plus 1 into 1, and x is the design matrix, epsilon is the error terms, and you have also seen that the estimate of beta is x transpose x inverse x transpose y. That also you have seen, where x is design matrix, y is data matrix, and this part we have completed in last class. So, if you see the slide, you see that there are n plus 1 observation for y, beta is k plus 1 into 1, these are the parameters of regression, and x is the design matrix, where the first column is all having 1 value, and then these are the data on k number of factors. Other way I can say k number of predictor variables x 1 to x k. Essentially, x is a n into k plus 1 matrix. And from sampling we know, the sampling theory we know that the estimate beta cap, this is a random variable. So, it has its expected value and variance component also. Suppose we want to know what is the expected value of beta cap, it will be beta, and that is what is unbiased estimation. Means beta cap is the estimate of beta, beta is the regression coefficient vector which is from the population point of view, and beta cap is the regression coefficient, the estimate of this vector from the sample data. Okay. So, it can be proved also that expected value of beta cap is beta. So, how can you do? You can write that expected value of beta cap equal to expected value of x transpose x inverse x transpose y, this. Then you can write expected value of x transpose x inverse x transpose, then y value is nothing but x beta plus epsilon, you are getting from here, and if you multiplied this, then you get x transpose x inverse x transpose x beta, x transpose x inverse x transpose into x beta plus x transpose x inverse x transpose epsilon. Now, x transpose x inverse x transpose x will be identity matrix I. So, this one will be expected value of beta plus x transpose x inverse x transpose expected value of epsilon, because this is coming out of expected value, this is the fixed values. So, beta being a constant parameter value, so it will be beta, and expected value of this error term by assumption is 0. So, this will be beta. Okay. So, you may be, then what is the variance of beta cap? Other way we can say covariance of beta cap. It can be proved that this will be sigma square x transpose x inverse, where sigma square is the SSE estimate of sigma square will be SSB minus n minus k minus 1. You already seen what is SSE, sum square error. Okay. So, we will discuss about SSE later on also. So, other way we can write how it is, it can be also proved. So, covariance of beta cap is nothing but expected, this is also expected value of your beta cap minus beta is the expected value of beta cap, this into beta cap minus beta transpose. So, you can see from the slide that we can prove that beta minus beta cap minus beta. So, you are writing this beta cap is x transpose x inverse x transpose y. Now, you are putting the same way when we calculate mean value, that this one, and then you found beta plus of this, and beta and this beta is cancelled out. So, you are getting beta cap minus beta is x transpose x inverse x transpose epsilon. Here you have seen x transpose, this is basically beta and this one is this. Now, this beta minus beta is cancelled out and this remains. So, now what will be then, that beta cap minus beta transpose, this will be transpose of this, and this quantity will be this transpose x transpose x inverse, and here x will come, this x will come, x transpose is x, epsilon transpose is there, x transpose on x minus inverse 1 is this, because it is symmetric matrix. So, then your expected value of beta cap minus beta and beta cap minus beta transpose, this is nothing but expected value of x transpose x inverse x transpose epsilon transpose x transpose x inverse x transpose x inverse. Okay. So, this is the fixed one, this one is also fixed quantity. So, if you taken out all those things, then ultimately you will be getting expected value of epsilon transpose into this x transpose x inverse x transpose x into x transpose x inverse. Now, this quantity become I, this quantity is what, sigma square, this quantity becomes sigma square. So, sigma square x transpose x inverse. So, that means essentially we got beta cap which will be multivariate normal basically, because there are so many, and it will be n, there are k plus 1 number of beta values, and then its expected value is beta and covariance matrix is sigma square x transpose x inverse. So, this is known as sampling distribution of beta cap. Okay. And I already told you that the estimate of sigma square will be this, which is nothing but SE square coming out of the error terms. Now, let us see that from sampling distribution to that test of individual regression coefficients. Here the concept is individual regression coefficient and group of coefficients. First we will discuss on individual regression coefficients. How many coefficients we have? We have beta 0, beta 1 to beta k, that is k plus 1 individual coefficients. We want to test every coefficient whether they are significant or not. That means, we want to test beta j for j equal to 0, 1, 2 to k. Here test means hypothesis test. test means hypothesis test. So, you have seen earlier that hypothesis test means there will be null hypothesis, there will be alternate hypothesis. Our null hypothesis is beta j equal to 0, j equal to 1 2, 0 to 1 2 like k, and beta j not equal to 0 is the alternate hypothesis, and obviously for at least one j, for at least one j. But here we are interested to test individual parameters. So, this is in total hypothesis test for totality, that whether this part under model adequacy test I will discuss again. But in this case, suppose if I consider only the jth regression parameter, then this is not applicable. Suppose the beta 0. So, we want to test beta 0, then H 0 is beta 0 equal to 0, H 1 is beta 1 not beta 0 not equal to 0. Similarly, beta 1 equal to 0, beta 1 not equal to 0, like this. So, individually we are testing here. So, general term H 0 beta j equal to 0, H 1 beta j not equal to 0. What we test statistics we will use here? We will use a statistics called T statistics here. Suppose we create a statistics like this, which is beta j, this is the random variable, estimate value minus expected value of beta j cap divided by square root of variance of beta j cap. This is T distributed because you have seen earlier that this from standard from central limit theorem, this can be Z distributed also, provided sample size is large, and as the variance of beta j, these are all estimated one, exact not known. So, we will go for Z to T distribution. Okay. So, this is tested, this is true when H 0 is true, means beta j equal to 0 or H 0 is true. As a result, we say this is T 0. So, this T 0, this follows T distribution when H 0 is true. Now, this can be written like this, beta j cap minus expected value of beta j cap, already you have seen this is nothing but beta j. Now, variance part you have already seen that sigma square, we have seen that covariance of beta cap equal to sigma square x transpose x inverse. So, this can be written like AC square, if we assume that the estimate is AC square, and into this, suppose that C 0 0, C 1 1 2, C k k, and this side also, that is C 0 1 like this. The off diagonal elements are the variance component. So, this C 0 0, all those things what I am saying, this is the component of x transpose x inverse. So, C 0 0 AC square, C 0 0 AC square will be that variance of beta 0 cap. Similarly, C 1 1 AC square will be variance of beta 1 cap. Like this, C j j AC square will be variance of beta j cap, and obviously j stands from 0 to k. So, what we write then that variance of beta j cap is sigma 0 sigma square into C j j. Now, the sigma square estimate is AC square. So, we are writing this as AC square C j j. So, and under H 0 beta j equal to 0. So, this quantity becomes 0. So, T 0 become beta j cap divided by square root of AC square C j j. Please keep in mind C j j is the jth diagonal element of x transpose x inverse. that is Cjj jth diagonal element of X transpose X inverse. Okay. Now, what you will do? You all know that hypothesis testing procedure. So, you calculate T 0. This follows T distribution with certain degrees of freedom. That degrees of freedom here is n minus k minus 1 degrees of freedom, because this is the error degrees of freedom n minus k minus 1. So, if you create a T distribution curve like this, and suppose that it should be a two-tail test, this side alpha by 2, this side alpha by 2, then this is T alpha by 2 n minus k minus 1, and this is minus T alpha by 2 n minus k minus 1. So, if the absolute value of T 0 is greater than T n minus k minus 1 alpha, alpha usually will be 0.05, then we can say the corresponding beta j parameter is significant. It is not 0, it is not 0, it is far away from 0. Okay. So, this is the test. This test is also known as, you just see. So, sorry, I have done one mistake, that is alpha by 2. Okay, alpha by 2, because it is a two-tail test. Please remember, when it is two-tail alpha by 2, when it is one-tail alpha. So, see the slide also. So, this type of testing is called marginal or partial test. Individual regression parameter is tested here. Suppose I say that y equal to 50 plus 2.05 x 1 plus 3.6 x 2, maybe minus 0.46 x 3 plus error term. Then what we are saying, beta 0 equal to this, beta 1 equal to this, beta 2 equal to this, beta 3 equal to this. So, by this test we are saying that whether this beta 0 50 is essentially 50 or it is basically nothing more than 0. So, as a result, what you are doing, you are just finding out the beta values. Suppose beta 0, beta 1, beta 2, beta 3 here, these estimated values. These values are nothing but here 2.05, 3.6 minus beta 1, beta 0, beta 1, beta 2. So, this is 2.05, 3.6 minus 0.46. These are the estimate value. Okay, value, estimated value. Now, you are finding out the standard error of beta j, let it be beta j cap. So, suppose I without doing any calculation, suppose we know that the standard error is here 4.0, here 0.50, here 1.20, and here may be 0.04. Then what will be the t value? T 0 value will be estimate divided by standard error. So, 2.05 by 4, it is almost 0.48 kind of thing. Then beta 0 is 50, I am extremely sorry, 50 by 4 means it is 12.50. 2.05 by 0.5 means it is 4.10. 3.6 by 1.2 means 12 into 3, it is almost 3, and 0.40 by this, I think this is your 100 you multiply, then it is 4, and if you 140, then it is almost 80, and this is minus 80. Now, if you compare, suppose your alpha is 0.05, then you compare t. Suppose your sample size in this example n equal to, let it be 50, and what is the k value? K value is, that means 1, 2, 3, k plus 1 is 4, k equal to 3, k plus 1 is 4. So, that means then n minus k minus 1, this value will be 50 minus 4, that is 46, and alpha equal by 2 equal to 0.025. So, find out this value from the statistical table. If this value, usually I think this value will be maybe around 2, this value will be around 2. So, see, this is 12.50, this is 4.80, this is 3, this is minus 8. So, absolute value of these, all these are more than 2, that means all the parameters are significant, individually significant. That is what is the individual parameter test. So, that means what I say, you have data set y, you have data set y, you have x. So, x1, x2 to xk, and then here y1 to y, in this data you have. From there, using beta cap equal to x transpose x inverse x transpose y, calculated this, you calculated the variance and all those things, and then from there you have got the equation. This, you suppose you got this equation, and this type of computation we have, and then this is the result, that all the regression coefficients are statistically significant. This is known as individual or marginal test. Okay. But many a times what happen, suppose you have a large number of data variables, suppose you do not want to test individual parameter, you want to test subset of variables. Suppose I have 10 x variables, So, maybe I want to test that the first 5, I have arranged them based on certain knowledge, that the first 5 are important and last 5 not important. But I want to be doubly sure that yes, last 5 is not contributing. So, in that case what happened, you want to test all those 5 regression coefficients simultaneously, and then accordingly reject the null hypothesis that this set of variables are not contributing or they are contributing. So, essentially the mathematics here is when I have k regressor variables, this is my model, and these are the things what is known to you, and then I have dividing into 2 parts. One is that beta 1 and beta 2, where beta 1 is r cross 1, r number of variables, and as I have p number of parameters to be estimated, where p is equal to k plus 1, then p minus r cross 1, this number of variables we are partitioning. That means, what you are doing, you are partitioning x, which is basically x1, x2 to xr to xk. You are making 2 partition here. This side you are saying x1, and this one you are saying here r number of x variables, and here then what happen, total is k minus r number of x variables are there. Okay. Other way actually, but please remember there is x0 also, x0 which assumes 0 all the time. Okay. So, this partition from the beta point of view we can write, just one will be added only. Suppose beta is beta 0, beta 1 to beta r to beta k. Okay. So, we are taking first r cross 1, and then if it is r cross 1, then this let it be r minus 1, and then remaining p minus r, where is p is equal to k plus 1 minus r. So, these two, this side is capital beta 1, this is capital beta 2. So, that is what is denoted here. Here you see beta equal to beta 1 beta 2 like this. Now, your test is that this r number of variables or r number of regression coefficients here considering x0 I am telling, r number of regression coefficients are not significant, then h0 is beta 1 equal to 0, and obviously alternate hypothesis will be h1 beta 1 not equal to 0. So, then what you can do, you can write down the regression equation in this fashion. Y equal to x beta plus epsilon is equal to nothing but x1 beta 1 plus x2 beta 2, because you see this partition will give you this. So, as a result what happened? As a result what happened, if h0 is true, suppose h0 is true, then this part become 0 and y will become, reduced model will be y equal to x2 beta 2 plus epsilon. So, that is what is written here, reduced model is y equal to x2 beta 2 plus epsilon. So, essentially what happened then, we have a full model which is y equal to x beta plus epsilon, and we have reduced model where we are writing x2 beta 2 plus like this. So, ultimately here in this model, as x1 beta 1 term is not included, so that means error term here will be more than error term here. Okay, so the different, that means the sum, using this model what you will get SSE, or suppose using this model you will get SSE reduced model, then what will happen, this SSE reduced model will be more than this, and the difference is contribution of this to the error, and if that one is significantly contributing, then H0 will be rejected. So, what is being done here then first we calculate MSE, what is mean square error, and this will be nothing but your SSE divided by n minus k minus 1, and it will be using full model, that means the first model. Now, you have used the second model, reduced model, and what you are getting, you see you are getting beta 2 cap x transpose x inverse x transpose y, here x2 is there only. So, go to slide and see the slide. So, beta cap equal to x transpose x inverse x transpose y in the full model. Now, reduced model beta 2 cap will be x2 transpose x2 inverse x2 transpose y. So, then we will get the SSR beta 2, that one will be beta 2 cap transpose x2 transpose y. From previous model we have seen beta 2 x2. Okay. So, ultimately, show the slides. Hello. So, beta 2 is x2 this, and SSR beta 2 is this, and obviously here with p minus r degrees of freedom, because you have not taken r number of regression coefficients, this one total p r is taken out, and then what is the SSR of beta 1, that is sum square regression beta 1 given beta 2, this will be the full SSR minus the SSR explained by this reduced model. So, SSR beta minus SSR beta 2. If this one is significant, then we will reject H0, that beta 1 equal to 0 will be rejected. Okay. This beta 1 equal to 0 will be rejected. So, you are creating F statistics here by saying that F0 equal to SSR beta 1 given beta 2 divided by degrees of freedom and then your MSE. So, what will be its degrees of freedom? If this one, or I can say mod of this, I think this it will be always positive. So, if this is greater than f, what is the degree of freedom numerator? R, degrees of freedom denominator n minus k minus 1 or n minus p, and if we create a alpha significance level, if this is the case, that means f 0 equal to this greater than this, reject H 0. That means we have considered that big beta 1 equal to 0, that is not correct. That means those variables are contributing. Okay. So, so I will just brief you little bit more here related to the individual regression coefficient. I have given you the hypothesis test, but the confidence interval is another important concept. So, we have seen that beta cap or you can write beta j cap minus beta j by variance, that is A c square C j j. This follows T distribution with n minus k minus 1 degrees of freedom, where n k p equal to k plus 1. So, you can write it n minus p also degrees of freedom, and then I have already told you that this is plus T n minus k minus 1 into alpha by 2, and this side will be minus T n minus k minus 1 alpha by 2. Then this quantity will be in between this. Again under H 0 beta j equal to 0. So, beta j cap by root over A c square C j j, this will be lying in between this T minus alpha by 2 n minus k minus 1 T alpha by 2 n minus k minus 1. So, beta j cap. Okay. Now, we want the interval for beta j. So, we will not put 0, this we will not put 0, we will keep as it is. Under H 0 it is 0, that is why test we have done. So, we will write this minus beta j. Understood? We want interval for beta j. Then this quantity will become beta j cap minus T n minus k minus 1 alpha by 2 root over A c square C j j, and this will be beta j cap plus T n minus k minus 1 alpha by 2 and root over of A c square C j j, where C j j is the jth diagonal element of the matrix X transpose X inverse. Okay. So, with this I will show you one example. Suppose beta is like this, from some data we got beta is like this. We will construct a 95% confidence interval for the parameter beta 1 in example. This is basically example from a book, and now beta 1 is 7 point this, and because and sigma square is this was also calculated earlier, and see that the C11, that is the X transpose X inverse, that this is this. So, we find that that means the beta 1 cap minus the 2.16 into this one beta 1 cap minus T 0.025 113 degrees of freedom. So, 3 plus 1 4, 3 the 2 plus 1 3, that means 16 minus 3, the 13 degrees of, that means sample size was is 16 here, and this follows like this. So, beta 1 cap you are writing like 7.62129, T 0 point this is 2.16, sigma square is this 260 on this, C11 from the X transpose X inverse, that particular part into 10 to the minus 3 less than equal to this value, and finally, you are getting this type of confidence interval. Now see that in the confidence interval there is no, this is positive to positive, one sided, there is no 0 in between. So beta 1 is statistically significant, means it is not 0. And from the hypothesis testing using t value also, you will find that you will reject the null hypothesis that beta 1 equal to 0. So thank you very much, and it is again taken from this Montgomery book, and also my earlier lecture, NPTEL lecture on applied multivariate statistical modeling. Thank you. I hope that you have understood the concepts.